In this class, we will discuss three problems from the end of the chapter in the first edition of Kleppner. So this is problem 10.3. The harmonic oscillator is being discussed in chapter 10 in the first edition. Let's consider this problem. In an undamped free harmonic oscillator, the motion is given by x equals a sine omega 0 t. Okay, so in the previous discussion of ideal harmonic oscillator and damped harmonic oscillator, we used a cosine function, but we know that any sinusoidal motion can be represented equally by a sine function also. So in this particular problem, a sine function is chosen for an undamped harmonic oscillator. The displacement at any time t is given by a sine omega 0 t. So let us say displacement at any time t is, amplitude is a, sine, angular frequency is omega 0 t. Okay. Okay, now this is for an undamped oscillator. Displacement is maximum exactly midway between the zero crossings. What does it mean? I have drawn, consider this figure here. In here, this dashed line represents undamped oscillator. Okay, so I have drawn only first half cycle of this sinusoidal function. Okay, we know, we are familiar with sine function. This is the first half cycle. Here you can see what is meant by zero crossings means here the graph is plotted with x displacement along the y-axis and the phase angle, that is omega 0 t, along the x-axis. I'm not saying phase constant. Phase constant here, initial phase is 0, but omega 0 t represents the angle, phase angle, the argument of sine function. That omega 0 t is plotted along the x-axis, so it's essentially angle along the x-axis. We know that a sine function in the first half cycle, the sine function becomes maximum at pi by 2. So zero crossings means the points at which a function crosses the x-axis. It becomes 0. At these 2 points, the value, when it crosses the x-axis, the value of the function becomes 0. Okay. So these are x equal to 0 and x equal to, omega 0 t. Along the x-axis we are plotting omega 0 t. So omega 0 t equal to 0 here, omega 0 t equal to pi here. These are the zero crossings. Okay, and the peak of the function is at pi by 2. It is exactly midway between the zero crossings. Zero crossings are at omega 0 t equal to, angle is equal to 0 and angle is equal to pi. And the maximum occurs at pi by 2, exactly midway. This is the situation in an undamped oscillator. But coming back to the question, in a damped oscillator, the motion is no longer exactly sinusoidal. We know that in a damped oscillator, the amplitude will not be constant, it will be exponentially decreasing. So there will be oscillation. In the case of, we know in a damped oscillator there are three situations: underdamped, overdamped and critically damped. And in this underdamped case, there will be oscillations. But these oscillations are not sinusoidal. It's not exactly sinusoidal because the amplitude is no longer constant. The amplitude will be exponentially decreasing. We have seen the plots of the position at any time t for a damped oscillator. So here what happens is, when you look at it carefully, the maximum is advanced before the midpoint of the zero crossings. That means here you can see that the solid line in this figure, the solid line represents the first half cycle of the damped oscillator. Okay, so when the amplitude will be exponentially decreasing, what happens is the maximum occurs even before the midpoint of the zero crossings. Okay, that is why we say that maximum is advanced before the midpoint of the zero crossings. Okay, it occurs earlier. That's the meaning of saying advanced. It occurs earlier than that in a damped oscillator. So you can see here it's drawn to a larger proportion. So here the maximum occurs here at this point. Okay, and we don't know where it is, but the difference between the angles for an undamped oscillator, where the maximum is at pi by 2, for a damped oscillator it is slightly earlier. Let us say the difference between the angles is phi. Okay, so we have to show that. So the idea is that for a damped oscillator, the maximum of the function of the displacement occurs uh, before the before the midpoint of the zero crossings. It's not exactly midway between the zero crossings. It occurs before. So how much before? To what extent it is earlier than that of it for that of an undamped oscillator? So here the problem, we have to show that the maximum is advanced by a phase angle phi given approximately by phi equals 1 by 2q, where q is very large. And also we know q is the quality factor or q factor. So we assume that q is very large. Okay. We know that quality factor, I will write it here, quality factor is omega 1 by gamma, where omega 1 is the angular frequency of a damped oscillator. But if damping is very small, then we can say omega 1 is approximately equal to omega 0, and we can write it as omega 0 by gamma. Okay, so here in this problem it is stated towards the end that where quality factor is assumed to be large. So we are considering this phase difference, that means between undamped oscillator and damped oscillator. What is the phase difference where it becomes maximum, where the displacement becomes maximum, and that phase difference is approximately given by 1 by 2q. And what is the approximation? In the limit when q is very large, when the quality factor is very large. And when does quality factor becomes very large? When the damping is very low. See, the definition of quality factor is q is equal to omega 1 by gamma. So when gamma is very small, when the damping is very small, quality factor is large. So here we assume that the damping is small. But when the damping is small, we know that the angular frequency of a damped oscillator omega 1 is approximately equal to that of an undamped oscillator. Okay, so this is the assumption. We assume that quality factor is very large. Okay, so therefore we also assume that omega 1 is approximately equal to omega 0. This is the approximation under which we are going to do this calculation. Okay, we have to show that the phase difference shown in this figure is approximately equal to 1 by 2q, where q is the quality factor. Okay, so let us start with this expression for the undamped oscillator. So I will put a suffix here u to show that it is undamped oscillator. Okay, so similarly, what is the expression for the damped oscillator for the displacement at any time? Again, amplitude is this time it's not constant. It is a raised to minus gamma by 2 t, gamma by 2 times t, where gamma is the damping constant. Sine, we have to write omega 1 t, but omega 1 is approximately equal to omega 0, so we can say omega 0 t. Okay. Now we want to find the conditions for the angle. We have to find the angle at which the displacement becomes maximum. So it's a standard way for undamped oscillator. For a sine function it is pi by 2, but let us see how we actually do this. So when x, the function x becomes maximum, its derivative becomes 0. Okay, so how do you do this calculation? Let us repeat this calculation which we already know for undamped oscillator. Okay, so for undamped case, how do we get this maxima at pi by 2? Okay, so at the maximum position, the rate of change of displacement will be 0. So for undamped case, take the displacement and find the derivative. So d by dt of xu. And for undamped case, what is the derivative? A is a constant. Sine omega 0 t, its derivative is cos omega 0 t multiplied by the constant omega 0. So we have cos omega 0 t. So what are the positions at which d by dt, or what are the angles at d by dt of xu is equal to 0? So which means this right hand side, a omega 0 cos omega 0 t is 0. We have to equate it as 0. But then a and omega 0 are non-zero. So the condition is that cos omega 0 t equals 0. Okay. What are the angles at which cos omega 0 t becomes 0? Omega 0 t, the angle should be it can be pi by 2, right? It can be 3 pi by 2, phi pi by 2, etc. Okay, so the first angle at which this cos omega 0 t becomes 0 is pi by 2. This is derivative of xt. So derivative becomes 0 at pi by 2, 3 pi by 2, etc. That means the function x becomes maximum at maximum in the two directions, maximum in one direction, maximum in the other direction at pi by 2, 3 pi by 2, etc. So in the first cycle, if this maximum occurs at pi by 2, you can see it here at this point, pi by 2. So this is how we get the maximum at pi by 2 in the first maximum is at pi by 2, or in the first half cycle for the undamped oscillator. So let us repeat this calculation for the damped oscillator. Okay, damped oscillator, we know the displacement. So let us see at what point the displacement becomes maximum. So for the damped oscillator, okay, so let us find again the derivative of the displacement, d by dt of damped oscillator is, so there are two time dependent terms here. The displacement is a e raised to minus gamma by 2 into t sine omega 0. So we have to take the derivative of the two terms. So let us do it. So first function into derivative of second function. So a e raised to minus gamma by 2t, first function, into derivative of second function. Second function is sine omega 0 t. Its derivative is omega 0 times cos omega 0 t. Then derivative of first function. So a is a constant. Okay. Then e raised to minus gamma by 2, there is a minus sign here. Gamma by 2 times e raised to minus gamma by 2t. Okay. And then sine omega 0 t. Okay. I will take common terms outside. So what are the common terms? A is common, e raised to minus gamma by 2t is common, into omega 0 cos omega 0 t minus this gamma by 2 is there, sine omega 0 t. Okay, and then equate this to 0. So d by dt of the damped displacement of damped oscillator equal to 0 implies the whole term on the right side is 0, but a is non-zero, e raised to minus gamma by 2t is non-zero. So the term in the bracket, square bracket, should be equated to 0. Okay, so this omega 0 cos omega 0 t minus gamma by 2 sin omega 0 t equal to 0. We can take one term to the right side. Okay, and we can say, we can write it like this: omega 0 cos omega 0 t. Okay, this is at the maximum displacement, right? So maybe we can put a suffix maximum here. Okay, this is equal to gamma by 2 m, maximum, or m we can put sine omega 0 t m. M stands for maximum. Okay, so here I will take this ratio sine omega 0 t m by cos omega 0 t m. It's equal to what you get, 2 times omega 0 by gamma. So what is this 2 omega 0 by gamma? We know that quality factor is equal to omega 1 by gamma, which is approximately equal to, in this case, omega 0 by gamma. So here we can write the right hand side as 2 times quality factor. Okay. Now let us make an approximation. From this figure, we know that this wherever this becomes maximum, okay, here, this point, wherever it becomes, whatever be the point at which this undamped oscillator becomes maximum, it's very close to the maximum of the damped oscillator and slightly less. This angle here is slightly less than pi by 2. Okay, let's take the difference as phi. So we can say that this angle, where it becomes maximum, so let omega 0 t, this is the angle at which the undamped oscillator, the displacement becomes maximum. Let this angle is equal to pi by 2 minus phi. Is this clear from the figure? The angle at which the undamped oscillator becomes maximum is pi by 2. The angle at which damped oscillator becomes maximum is close to pi by 2 but slightly less than that. It becomes maximum earlier than pi by 2, the damped oscillator. So let us, this angle is we have obtained as omega 0 t suffix m. That is the angle where it becomes maximum. And let this angle as, let us take it as pi by 2 minus the difference phi. Okay, then what about our equations, and where phi is very small, where phi is very small compared to 1. Okay, it's a very small angle. So then we can make an approximation. What about sine omega 0 t? What about the numerator in the above equation? Sine omega 0 t m becomes sine pi by 2 minus phi, right? Instead of omega 0 tm we substitute pi by 2 minus phi, and sine pi by 2 minus phi is cos phi. Okay, when phi is very small, this is approximately 1. We know that when phi is very small, cos phi tends to 1. Okay, so the numerator becomes 1. What about the denominator? Denominator is cos omega 0 tm. This is equal to cos pi by 2 minus phi, right? Cos pi by 2 minus phi is sin phi, and when phi is very small, sin phi is approximately phi. Okay, so let's come back to this equation. In this equation, okay, we get this result that when you put the approximation that phi is very small, okay, and this condition happens when the damping is very small. Okay, that means when gamma is very small, that is Q factor, quality factor is very large, right? Omega 1 is approximately equal to omega 0. Already we have put omega 1 approximately equal to omega 0 in all the equations in the damped oscillator. So we are under this approximation already. Okay, now so the numerator is what? Numerator is sin omega. So numerator is approximately 1, and denominator here is cos omega 0 tm, and that's approximately phi. So the equation we can rewrite as, left hand side we can rewrite as 1 by phi. This 1 by phi is equal to 2q, which means the difference phi is equal to 1 by 2q. So that proves our result. Okay, we have to show that difference in the phase is 1 by 2q. So we have got that result. Okay. From the figure also it's clear. It's very close to pi by 2 but slightly less than pi by 2. Okay, this is the way the undamped oscillator peaks. Not exactly in between the two zero crossings but slightly earlier. And that in the case of low damping, that difference in the phase angle is approximately 1 by 2q. Consider the next problem, problem 10.4 in Kleppner edition 1. The logarithmic decrement delta is defined to be the natural logarithm of the ratio of successive maximum displacements in the same direction of a free damped oscillator. Here what means by free is there is no force acting on it. Okay, it's a damped oscillator, but okay, there is this damping force acting on it, of course, but there is no driven force acting on it. Okay, so this will become clear. It's not a driven oscillator. That's the meaning of free oscillator. But that damping force, so other than damping force, there is no other driven force and driving force acting on it. Okay, it's not driven. There is no driving force. Yeah. Okay. So let us consider the next problem, problem 10.4 in Kleppner edition 1. The logarithmic decrement delta is defined to be the natural logarithm of the ratio of successive maximum displacements in the same direction of a free damped oscillator. Show that this delta, this logarithmic decrement, equals pi by q, where q is quality factor. Assume that q is very large. That means very low damping. Okay. Here what is meant by a free oscillator, free damped oscillator? Damped oscillator means a damping force is acting on it. Free means other than damping force, there is no other driving force acting on it. Okay, there is no force driving this oscillator. Okay, so this becomes clear when we consider forced oscillator. It's not a forced oscillator, that's meaning of free oscillator. Not a forced oscillator, but damped, its damping is there. Other than damping force, there is no driving force. Damping force, we know that opposes the motion, but driving force is something that causes the oscillator to oscillate. Okay, so that no such driving force is there. It's a free oscillator. That's the meaning of free oscillator. So we have to show that this logarithmic. So what is this logarithmic decrement? It's a ratio of successive maximum displacements in the same direction. I have drawn the displacements of a damped oscillator here. Okay, of course I have considered low damping, so it's still oscillatory, but not exactly sinusoidal. That means amplitude is not constant, amplitude is exponentially decreasing, as you can see. We have drawn this figure earlier also. So here this is maximum displacement in one direction. This is the maximum displacement in the other direction. Imagine an oscillation of a simple pendulum, let us say. Again it undergoes maximum displacement in the same direction. So this logarithm decrement means logarithm of the ratio of maximum, successive maximum in the same direction. Okay, a pendulum goes to the right, then it comes to the left, its amplitude decreases, its displacement decreases, again it goes to the right. So take two successive displacements to the right and take the ratio. That's the meaning of successive maximum displacements in the same direction. Okay, and take this ratio, and natural logarithm of this ratio is called logarithmic decrement. So here we are going to, I will mark the two maxima here. Let us consider this is the first maxima, let us say at the time. Okay, here we have again assumed that angular frequency of the damped oscillator omega 1 is approximately equal to omega 0. In other words, we have assumed that this gamma is small, damping is small, and quality factor is very large. In that condition, angular frequency of the damped oscillator will be approximately equal to the natural frequency of the oscillator, or that of the undamped oscillator. So let us say this at this time, the angle here is omega 0 t1, or the time at which it becomes maximum is t1. So angle is omega 0 t1, and then it undergoes maximum in the opposite direction. Again the maximum in the same direction, next maximum in the same direction is here. The time, let us say it is t2, so the angle is omega 0 t2. Okay, so let us write down the two displacements. The displacement x1 at the time t1 is okay, what is the displacement at any time of a damped oscillator? Amplitude A, amplitude is not a constant, it is minus gamma by 2 into t. So it's the time is here is t1, and let us say it's a sine function. So I have drawn here a sine function. Sine omega, we have to write actually omega 1, but omega 1 is approximately equal to omega 0. So this is it, sine omega 0 t1. And let us assume that the initial phase is 0. And at the time, next maximum occurs at the time t2, and the maximum displacement is x2. It is e raised to minus gamma by 2 t2 sine omega 0 t2. Okay, let us take the ratio between these two amplitudes, higher amplitude by lower amplitude, x1 by x2. Then a will cancel. We have e raised to minus gamma by 2 t1 minus t2, then sine omega 0 t1 by sine omega 0 t2. Okay, now if the damping is low, or the damping we can say the damping is low, then we can say that the approximate angle between, that is this omega 0 t2, we can say that is approximately omega 0 t1 plus 2 pi. Okay, see, in the case of a damped oscillation, the motion is not exactly sinusoidal. Okay, so let us say this, we know that for example, if we consider the first half cycle here, we know that this the maximum between the two zero crossings is not exactly midway between 0 and pi. It's not exactly at pi by 2. There is it comes earlier. Okay, we know that the difference is, in the previous problem we have discussed it, the difference is 1 by 2q approximately. So, so this happens in successive oscillations. Therefore, between this maximum and this maximum, the angle need not be exactly 2 pi. So we can say it's approximately 2 pi. So we can say omega 0 t1 plus 2 pi is omega 0 t2 in an approximate sense. Therefore, if this is true, then we can say, if we take sine function, sine omega 0 t2 is approximately sine omega 0 t1. Okay, sine omega 0 t1 plus 2 pi is sine omega 0 t1. So these two terms in the ratio sine omega 0, this is actually t1 in the numerator, sine omega 0 t1 and sine omega 0 t2 will cancel. So what is our ratio of amplitudes? x1 by x2 is e raised to, okay, we know that t2 is greater than t1. t2 is later time, right, in the figure. t2 is a later time and t1 is the earlier time. So t2 minus t1 is the positive value. So we can take a negative outside here from the exponential factor. So we get gamma by 2 into t2 minus t1. And this t2 minus t1 is approximately the time period, we can say, time period of the undamped oscillator. Okay, t2 minus t1. This because t1 is the time at which it peaks here. t2 is the time at which it again peaks. So the time interval between two successive peaks is the time period, right? So this time period, t2 minus t1 is the time period, and we assume that this is also the time period of this. This is the time period of the damped oscillator. Exact t2 minus t1 is exactly the time period of the damped oscillator, and this may be different as we go along, as the oscillation proceeds. The next two successive amplitudes need not have the same time. Okay, but in the case of low damping, this t2 minus time interval is approximately equal to time interval of the undamped oscillator. Okay, and this is equal to what? 2 pi by omega 0, where omega 0 is the natural frequency of the undamped oscillator. So here I can rewrite this as e raised to gamma by 2, okay, into t0, that is e raised to gamma by 2 into 2 pi by omega 0. 2 will cancel, so e raised to pi times gamma by omega 0. What is this gamma by omega 0? Okay, we know that quality factor is defined as omega 1 by gamma, which is approximately omega 0 by gamma, because when the damping is low, then omega 1 is approximately equal to omega 0. So quality factor for low damping we can define as omega 0 by gamma. So in this expression, the exponential factor, we have e raised to pi into gamma by omega 0, which is reciprocal of quality factor. So e raised to pi by q. Okay. So x1 by x2 is equal to e raised to pi by q. Right. Now take natural logarithm on both sides. Therefore, natural logarithm of x1 by x2 is pi by q. And this natural logarithm of successive amplitudes of successive amplitudes of displacement, or amplitudes of successive displacements, is called the logarithmic decrement. Okay, delta. So delta is pi by q. Okay, again notice that this expression for delta is valid in the approximation of low damping. That is, when quality factor is high, gamma is low. When omega 1 is approximately equal to omega 0. Throughout we have used omega, instead of omega 1 we have used omega 0. Okay. So that is the idea of quality factor, and you have to remember this equation delta equal to pi by q, because in some problems logarithmic decrement will be given and you will have to calculate other parameters of a damped oscillator.